Alice. Can we start on my right? Kent and then Dauka, and we'll come this way.
Thanks very much, Hila. Could you go back to the slide where you did the mirror flip between Alice and Bob? Yeah.
Will that one do?
Yeah, that's great. So this may be a superficial worry, and you can easily brush it aside. But the superficial worry is that you've made this look more time symmetric than many people would think it is by putting Alice on top of the experiment. I mean, people normally think, so Alice does something and she sets the polarizers here, so what she does is in the past of that, and Bob can suddenly...
No, good comment. So if I've got this right, your worry is that here, here Alice is actually in the past of this apparatus.
Yeah.
Here, under the flip, she'll be in the future.
Yeah.
Yeah, no, good. You're absolutely right. And so to describe this in a more precise way, in order to avoid this, you need to think of this whole thing as like one of those kind of Bayesian networks, which we reach into from the outside. And so the way to think of it is to think of the initial thing before I put the mirror in. So that one. Think of that one as a space-time way of representing what I had in the different kind of diagrams in the middle section of the talk, where I had a picture of a device that we could reach into at 2 points. Suppose I put in something on here like a blue spot, and a blue spot was supposed to represent an intervention point where we could, and this is I mean, getting very close to notions that people use a lot in the philosophy of causality these days, where you have this notion of reaching into a system from the outside to set the value of a variable. So that's the kind of notion I'd use. And then when I do that, I would say, look, what we've got in the top half here can be read as a space-like diagram with intervention points here and here. So what I'm doing in effect is taking the experimenters out of the picture explicitly in order to avoid precisely a worry. I mean, you're absolutely right, but it's not. I don't think it leads to any deep problems.
Faye?
But outside the picture means outside of space and time. Outside of space-time. So. Alice, you're intervening from outside space-time.
No, I don't think it does mean that. I mean, as people talk about causation in an interventionist way, people say, well, I mean, I'm trying to remember a quote which is often quoted by me, among other people, from the computer scientist Judea Pearl, who's an enormously influential person in this literature. And what he says is something like, look, when we use causal notions, we divide the universe into two. We think of the system, and then we think of the agent outside the system who can reach into the system and set values of the variables. But when we're doing that, of course, we're not thinking of the agents as being outside of space and time. They're just outside the particular system inside which we're considering the causal relations.
I'm just wondering if there isn't something deeper lurking here, which is that we're using sort of operational notions to define causality. And yet operationalism presupposes a sort of everyday existence, and in that the agents are necessarily time asymmetric, or so it would seem. So I'm just wondering if the last two questions are sort of picking up on that.
I mean, Raphael, I mean, I agree with you that our ordinary notion of causality has, I mean, the asymmetry of the ordinary notion of causality does come from our asymmetric perspective as agents, in my view. I think that's quite right. But I also think that it's not relevant to what I'm doing here. Another way, I think, maybe this would, maybe Adrian would find, and Faye would find this better. Another thing I could do here is to take out agents completely and just have some time-symmetric coin-tossing device, which is choosing the values of the the settings here. And as long as that's time symmetric, it'll look exactly the same in the mirror as it does here. And we'll still have a pattern of correlations to be there to be explained, and the point will be that given that the correlations in this space-like experiment are the same as the correlations, in the time-like experiment are the same as the correlations in the space-like experiment. The symmetry represented by the mirror is a useful one.
But I'm just thinking that if in fact you have an agent-free way of describing causal influence, that's very interesting. But to the extent that it does presuppose the idea of agent, I'm just wondering if there isn't some inherent contradiction between the notion of agent and the notion of time symmetry.
Raphael, I'm very sympathetic to the point you're making, but I don't think it's immediately relevant to the point that Adrian was making.
Okay, I do, but
because I think I think you could leave causality out of this altogether. Go to the framework where you've got some randomizer which is selecting the settings here and here for that matter too. What you've then got, looking say at the original time-like case, is you've got a great list of correlations. Where on the list you've got the setting, the output of the setting randomizer, the output of the input randomizer here, the output randomizer, and the setting randomizer here, and then the correlations given in the time-like case by Marlis's law, they're reflected in properties of that big list of results. You've got exactly the same kind of list of results for this space-like version of the experiment up here. And the point of this little mirror diagram is to show in this, what I was hoping would be a simple way, how allowing the setting randomizer here to be correlated with the value of a property here. Notice I say correlated, I didn't say cause, I'm leaving cause out of the picture. I'm just allowing a correlation between the output of the setting randomizer here and the value here. Plays exactly the same role in explaining the correlations up here as the corresponding thing does down here. Which the corresponding thing here, we can also describe it just in terms of correlation. We can leave causation out of the picture altogether, if you'd like to do that.
Okay, I'm going to suggest we move on then. Well, moving in the same way then, next up I think is Peter Lewis and then Matt Leifer and then...
Okay, I'm not going to be arguing the same dead horse. I want to see if I can locate the retrocausality a bit better. So I'm interested in what nature chooses means. Right? So with Bob there, nature chooses the channel. Well, ordinarily we'd say based on what Bob does. Right? Bob does something, and then that affects. Nature looks at Bob and makes a choice. Or in other words, there's a law, right? Yeah. Based on what Bob does. Yeah. Now what about Erotan down here? Right? Suppose the photons coming in are already in flight when the setting choice is made. Then Erotan makes a choice. Erotan has to be like precognitive.
Well, this is partly why I used the demon when I originally presented.
Yeah, because the demon has to be precognitive, right?
Yeah, exactly.
Yeah. So there's already, or if you want to, like we did up at the top, we put it in terms of a law.
Right. Well, it is
in terms of a law down here.
It is a law. It is a law.
Right.
I mean, it's just the quantum version of Marlis's law in effect.
And does it have a direction? I mean,
no, it doesn't. It's time symmetric. But that's that's why the fact that which we the once we get to the quantum case, And if we have discreteness over here, that's why we get this extra degree of control there. I mean, that's coming from the law. You're quite right. There is a law, and it's that law that tells us that in the case in which we have the daemon or a randomizer, then changes we make here will show up as changes here too. It's just a law-like fact that differences here have to correspond to differences here. In a way,
but not back to the.
No, not backwards. Yeah, yeah.
So setting here doesn't affect what the demon throws in.
But I mean, you know,
because on the output end we are tempted to talk about.
Yeah, but the basic point, the reason why there's this degree of control here is it's coming from the discreteness. So these issues of whether it's forwards or backwards, they're simply not relevant, because the mathematical fact about the number of options there are in one direction or the other is the same in both cases, given discreteness.
But it is retro. I mean, it is acting backwards. I mean, the choice of the demon depends on Alice's polarization setting.
Yeah.
So
Well. Yes. Well, if you were, I mean, you're quite right, Faye. There is a point here that if you assumed that the demon, I mean, I think as I originally presented it, I said something like, the demon can see this knob, so she can see what Alice has chosen. But if you set it up in a trickier way, in which Alice made her choice instantaneously, so there was nothing there for the demon to see in advance, then it would be true that in making this choice, Alice would be having a retrocausal effect on the demon. Okay. And so they were, but so there's this sense in which there's this sense in which the demon involves retrocausality, but you can avoid that by replacing the demon with a randomizer, and in the later stuff that will do just as well, I think.
Okay. Sorry, you want to follow up on that?
No, it's my question.
Another question. Okay. So Matt Leifer.
Okay, so I wanted to ask about, so that you gave an argument that causality doesn't necessarily imply signaling. And I agree with that argument as a response, to the fact that obviously the objection that they would cause paradoxes. But there's a more subtle version of the objection, which is to say that that argument you gave works, but it requires fine-tuning.
Okay, good.
So in this case, in the case of this bit flipper, it only works if the coin has exactly probabilities half and half. If it's altered by even epsilon, then suddenly you get signaling.
Yeah.
So how do you respond?
You're thinking of Rob Specken's stuff in fine-tuning. I think that's interesting. I think the symmetry that Ken and I are trying to get at in using this sort of diagram is helpful here too, because I think that the point is that the same thing that you're calling fine-tuning, which prevents retro signaling from Bob to Alice, or indeed in the case in which you have a randomizer prevents signaling from Alice to Bob, is the same thing that prevents signaling in the EPR experiment, whatever your story about the ontology in between. So I think, even if you're a quantum Bayesian, it's going to be true for you that if the outputs on Bob's side of an EPR experiment are not random, then you can use them to signal. So if Bob knows that his outputs are biased, then he can signal to Alice. That fact is independent of anything that you say about the ontology here.
Well, I think that one would accept, I think Rob is not here, but I think he would make a fine-tuning argument in that case too. So maybe not for quantum Bayesianism, but for the Bohmian account. Like the reason why he would reject the Bohmian account is because similarly it would require fine-tuning to operate.
Okay, well, I mean, as I read Rob's original stuff, it sounded like the label fine-tuning was supposed to be a negative one, which he wanted to apply to certain kinds of models, like the Bohmian one or retrocausal model. And then what I wanted to say in response to that is, no, look, if it's a problem, then it's a problem for everybody.
Well, I mean, so the quantum Bayesians wouldn't accept this notion that there are influences going in any direction, really.
They don't have to accept that. If Bob's outputs are non-random, we can build a signaling device for them. I mean, no. Suppose we have a version of this in which it's true of Bob's devices that 60% of the time the photon comes out of one channel and 40% it comes out of the other. Then we can build a signaling device.
Sure, but I mean, I'm not really sure how that applies to, say, quantum Bayesian argument, because in order for probabilities to be fine-tuned, there has to be...
Well, okay, so what I'm saying is it's just the probability. What needs to be fine-tuned are just the probabilities of the outputs.
I think
Ken wants a finger on this.
So one issue is you're comparing a 50-50 probability to a non-50-50 probability. And you're saying 50-50, that's fine-tuning. But from a stat mech perspective, actually it would be, from an entropic perspective, it would be actually the non-50-50, which you could argue that's fine-tuning, and in a maximum entropy case, you can't signal at all.
yes, but in thermodynamics there are non-equilibrium systems.
Sure, and you could say those are fine-tuned.
Well, I mean, I would still say that equilibrium systems are the fine-tuned ones in this sense, but the point is that if you use that thermodynamic kind of explanation, then you would expect to find systems out there which didn't have that property, the animals of non-equilibrium systems. So you'd expect to actually be able to signal those systems, because they wouldn't.
Even in a maximum entropy universe, can you say?
Well, they don't live in a maximum entropy.
Okay, so can we leave that for the moment? Next is Dustin.
So thank you very much for the talk. I think the overall message of your talk is brilliant, but I think that the new a priori argument that you try to give for retrocausality is inconclusive. And okay, the discreteness thing is an issue that one could discuss, but I think there's another objection which basically every version of quantum mechanics would agree, namely that a quantum measurement, or even just the act of polarizing a photon or electron beam, is an irreversible process, not in a fundamental sense, but in a thermodynamic sense, in the sense of entropy increasing. And this has nothing to do with collapse, but just, because you're separating the two parts of the two spinor components, and then which is already practically impossible to reverse. And then, of course, if you record it in any way, you have entanglement with the macroscopic environment and coherence and so on. And I think if you think about that, then it's really this irreversibility which somehow grounds or justifies this, if you want, causal asymmetry, meaning that the state of the system, after it passes the polarizer, is affected by your choice, but not before. So this choice would be not so much like kicking a billiard ball or not, which would be reversible if you think about this
Okay.
but more like taking a poison pill or not.
I think if you want to appeal to thermodynamic stuff and irreversibility, it has to be via. I think the only point at which it can really come in here is as a way of criticizing discreteness, a way of saying, well, it looks discrete, but in fact it's not really discrete, or at least we don't get the right sort of combination of discreteness and time symmetry. Because so far as I can see, the argument for thinking that controlling this left-hand knob controls a beable here, that argument doesn't seem sensitive to any of those thermodynamic kind of issues. Maybe you disagree, but as far as I can see, it's not. And then the argument on this side is, I mean, assuming discreteness, the argument on that side is simply, you know, a time reversal of the argument on the other side. And if you've got discreteness, it seems to me that the argument on this side has precisely the same sort of status as the argument on that side. As Peter said, it's just an appeal to laws. I think if you want to sort of appeal to that sort of thermodynamic stuff about measurement, it's got to be up here. It's got to be at the stage where you're saying, well, on the surface, if you just look at the results of measurement devices, it looks like the quantum world is discrete, but that's a mistake. Deep down underneath, we don't have discreteness. So it has to be that kind of argument, I think. But maybe I'm missing something.
So I'm not sure maybe if it should be located more on the discreteness part than on the time symmetry part, but I think if you're asking why does this state of the beam after it leaves the polarizer depend on my choice but not before, then the answer is because this is an irreversible process.
I mean, one thing I should perhaps add is that in normal circumstances, of course, there's no demon. In normal circumstances, we control the inputs but not the outputs. Now, the answer, if you ask why is there that asymmetry, that certainly has something to do with thermodynamics. It's because, well, maybe it's because we're asymmetric creatures, as came up in the early discussion, but it's certainly because we live close to a low entropy source, which we can exploit to get control over initial conditions. So there's certainly, you know, in the ordinary case, the thermodynamic asymmetry does make a difference to what we can control. But the whole point of thinking about the special case in which we have the demon or a randomizer here was to abstract away from that and think about cases in which our control over the inputs is just the same as our control over the outputs. Namely, we don't have it.
Okay, Nicholas Gissin had a finger on it.
Yeah. Yeah, on this picture here, I see that you assume or you use that these TR and TL are equal, tau L and tau R, which after this mirror field corresponds to a maximally entangled state of standard quantum mechanics. So how would you tell the story if it's a partially entangled state?
I'm sorry, I don't understand the question.
Well, you cannot. Well, you can also violate Bell inequalities with states which are not maximally entangled but partially entangled, where the correlation is weaker than in maximally entangled states. And that would correspond here. That's actually your tau L. I would assume that corresponds here in this picture. So before the mirror, that tau L and tau R are not exactly equal but related. And I don't see how to tell that story.
Well, I think Ken will be saying something in his talk about a story in which you have tau L and tau R. Ken, are you going to talk about this stuff?
Yeah.
But I'm not. I'm sorry. I still don't. I'm not clear enough about what the question is to be sure that Ken is going to answer it for me. Although, of course, that's what I'm hoping will be the question.
Okay, well, we're beginning to go on.
I will mention that tau L and tau R are not the same in this one. If you turn one knob, it turns tau L. Turn the other knob, the tau L. Turn the other knob, turns tau L. They're not the same.
Okay, we want to get to the end of the people who've been very patient. Lev Weidman, then Howard Barnum, and then Faye Alka. So can we squeeze and Brian Roberts too? So Lev, you're next.
Take me out of there.
Really?
I did talk. I think this slide is good, but on the next slide, I think we have this maybe move to the next slide for a second. Yes. Covarialism, time symmetry, discreteness, retrocausality.
Sure.
All these concepts are not, maybe if I go to your papers, they will be exactly defined. All these things are not very clear what they mean. And so my example, the example which I have difficulty, if you come back to the previous one, tau r, you can affect tau r by in some way. And now we say we proved retrocausality. The word retrocausality means that we change reality. Does tau r reality? So
that was realism.
What?
Realism was the assumption that tau r. Well, realism was the assumption that tau l is a beable. And
tau r, because tau.
Well, that's where you appeal to time symmetry. So if you've got a beable tau l, then time symmetry gives you a beable tau r, which stands in the relation to the stuff on the right in the same way. I mean, its law-like relation to the stuff on the right is the same as the law-like relation that tau l has to the stuff on the left, given that the left and the right are the time inverse of each other.
So you say we can influence what the input of the daemon?
Well, no, I didn't say that. I said we can influence tau r, which in some of Ken's models would be thought of as the polarization of the photon immediately before it gets to the right-hand crystal.
It's not like what I kind of saw in this picture, the two-state vector formalism. Tau L is a forward evolving, tau R is a backward evolving.
I think that the two-state vector formalism does fit this picture, but I don't want this picture to be as specific as that, because I want it to apply to other possible models where the beables are different things.
So, but then in this picture, tau R is not the state just before the beam split. Tau R is a different one. And what I would like for realism, that if it can influence past in some way, some measurable thing, if you can input some tau R is our invention. We put tau left tau.
It's not exactly our invention, because we already had tau L, and then given that we were assuming time symmetry, we didn't have any choice but to put in tau R too.
Causality, we should change some things. So the fact that we change polarization, this is not changing things. We should change results.
Well, no. You want to make a difference to something in reality, and here you can see. Look, I'm making a difference to that. For me, that's what causality is. It's the ability to reach in, change one thing, and have something else change in a corresponding way. And if this argument works, it shows that under those three assumptions, realism, discreteness, and time symmetry, we do have that ability with respect to things prior to our interventions.
So the realism tells that everything which you put here is real in some sense. This is because one realism that you have an outcome. This is what I thought.
Okay. Oh no, that's not what I mean. What I mean is that tau L should be thought of as a beable.
Okay. Brian Roberts?
I'm interested in the generality of this result. It's kind of similar to the question that Nicola asked. So assuming there's lots of different ways to have entangled states between two space-like separated regions. I mean, I'm willing, say I grant that this whole picture works in this particular context, and I'm just interested in knowing if I have entangled states across two space-like separated regions, and you can tell me if this is the wrong way to put it, does there exist a state corresponding to a region in the causal past of those two regions, which screens off the correlation? If there exists such a state, I can do your zigzag procedure where I go backwards in time, screen off the correlation, then forwards in time again. And the question, but then there's a precise mathematical question, which is, in general, if I have two, entangled states of some kind across these space-like separate regions, does there exist such a state in the common past? Of course, people have done some work on this, and my understanding is that it's somewhat of an open question whether or not such a state always exists. And so then I just ask, is this a reasonable way to put this mathematically as a general question? And is it really?
I think so. If I understood it, then I think it's a very good question to ask. Though I think that there may be a sort of tweak that you need to the question, because I think you may need to distinguish the question as to whether as it were, you get mathematically consistent descriptions of cases in which you have the entangled state without the thing in the common past. From the question as to whether, if that is mathematically possible, we have reason to think that there are actually any states of that kind instantiated in the world. I mean, because you could presumably have a picture whereby it was mathematically possible that we had these space-like separated, but not correlated via any sort of zigzag cases.
Yeah. So I'm just asking the second thing, because that's a prerequisite, it seems, of this account.
Yeah, no, exactly. No, you're absolutely right.
Okay. Howard, are you sure you want to fall on your sword?
Oh, yes. Well, no. I won't fall on my sword, but I'll just pass on my question.
Faye
has a finger.
Yeah, Faye, please. Yeah.
So just following up on that, on Brian's point, what about correlations which are not quantum but still, I mean, the maximally non-local correlations that people sometimes refer to as a PR box, for example, as being the set of non-signaling correlations which maximally violate the Bell. They violate the Bell, the Bell inequalities, but maximally, and are not realizable by any quantum model.
Good.
Can you tell some story like this for those correlations? Those
not so far as I know. I mean, I'm not proposing that there would be no. I'm not proposing that there's no quantum-like theory with sort of strange space-like correlations for which you couldn't tell this story. Insofar as I'm proposing anything, it's just that it's worth exploring the possibility that for all correlations of this weird kind that we find in the real world as a result of quantum theory, this theory does work. So that all the sort of real-world quantum reasons for believing in action to distance turn out not to be good reasons because of the Parisian zigzag. So that's the possibility that I'm interested in exploring.
So really one of those implications, you had the two implications that imply richer causality, and the first one is kind of an open question, is the bottom line.
So you mean later on where I've got the Bell and this argument? You're thinking... So is that... Yeah,
the quantum mechanics plus no magic implies richer causality. That's not quite an implication, is it? Because we need to know that such that it's always possible to...
Okay, good, yes. No, I see what you mean, yes. Yeah. But now I'm confused because I thought I got to that line just by logical manipulation on that line.
Yeah. You say no magic in any entangled.
Sorry, Brian. I'm confused. I'll just need to think about that.
Okay, we are up against our 3 o'clock, so we'll have a 5-minute break. But before that, please join me in thanking you very much.